organic matter with a very complex compound to lose lighter elements and break these long carbon chains into more simpler carbon chains, which is the transformation of from organic matter into oil. We need overburden, which is rocks above the the source rock that will create the temperature and pressure, and we need time. We need time to uh, this source rock can be exposed in a prolonged way in the suitable temperature and pressures so it can break these carbon chains. We also need uh, time to make everything work in the right way. You know, first you need to let me explain more a bit. But time is a very important part of this equation as well. Things cannot be too long and not too quick again. The second element is the reservoir rock. Basically, this is any type of rock that contains necessary characteristics to store and transmit fluids. And here you have some examples of the most common reservoir rocks, which is sandstones. Here is a hand sample in the thin section. And we are seeing here in blue is the empty space. We call that porous. Also the limestones, here is a core from the coquinas, from the pre-salt. And here is a thin section as well. And again, the pores are seen, you are seeing in blue. And these are the main conditions for petroleum accumulation. These rocks need to have empty spaces that we call pores. So it will be the space where the fluid will flow within the rock. And these pores need to be interconnected so the oil may flow through the rock. We also have a couple other reservoirs. It's not there are less the reservoirs occurs in a smaller percentage. For example, tight shales, uh, reservoirs of igneous rocks. But this is more specific. Just to give you an introduction. If you uh, if you guys want to, we can talk a bit later about that. But basically, the porosity and the permeability of these rocks depends of many things, but basically an interaction of the depositional system, put this in Portuguese, sorry, which is basically is the process that are creating these deposits. So basically that will let us, depending on the process, if the sandstone is well sorted or poorly sorted, if the grains are rounded or angular, all of that will impact the porosity and permeability. Sediment source, basically where these sediments are coming from. If we have a lot of different minerals that are not resistant, should I say that? Like quartz, they may be chemically alterated and become shale, the fine-grained sediments, and that may be within the empty space and they'll reduce the porosity. And also, we need to learn what was the post-depositional history of these rocks. If there was any cement or any dissolution or any other alteration that happened before the deposition of these rocks. Finally, we need a seal, which is a rock with low hydraulic conductivity, capable of retaining the liquid and gaseous hydrocarbons. So this rock will act as a barrier because, as I said before, the hydrocarbons will try to flow to the surface. And unless they found a barrier, which can be a seal rock, and they must have low porosity and low permeability. I have a couple examples of seal rocks. In this case, it's evaporites. This is a mining uh, of salt in Brazil. Here's an example of ore. But many other rocks can act like that, like shales, fine-grained siliciclastic rocks, fine-grained limestones, or even igneous rocks. Uh, any question? Um, so let's move on in a petroleum system, the process in a petroleum system. We talk a bit of the elements, but there are some processes that need to occur so we can transform organic matter into oil and we can accumulate those we call traps. Basically, the organic matter transformation occurs as soon as it is deposited on the ocean floor when it starts the diagenesis, and with the subsidence occurring in the basin, we have increasing temperature, we have increasing pressure, so organic matter lose the light elements uh, and becomes a kerogen. It's still a complex compound, but less complex than organic matter, and this is a precursor of oil, and this is still an immature zone. But with increasing temperature and pressure, we get into we call oil window, and by the increasing pressure and temperature, we are able, nature is able to break the carbon chains and transform kerogen oil. And this is the catagenesis. If this process is still going on, we may start to generate gas, and until we reach the metagenesis is when the gas loses the heavier elements and basically generates methane. And we don't want to go much further than that because that's when we start with metamorphosis and we burn all the organic matter. So basically the final quality of the oil depends on many factors, just the origin of organic matter. There are some organic matter that are more prone to generate gas, others are more prone to generate oil, but it also depends of this degree of thermal maturity as well as many other factors. This is not a simple equation. There's a lot going on in the subsurface, and the result of all of that uh, will say the final quality of the oil. And there are many ways so we can classify oil. Here's an example of the API classification. This is American Petroleum Institute, and basically they created a classification where uh, lighter oils, they have a higher numbers, and they are easier to extract from the reservoirs than the heavier ones. These require more complex procedures, and they all the derivatives from oil varies from each one of them. Um, there are also other types of classification depending on the quantity of sulfur, and again, this is all the result of a weight complex equation. The second process that I want you guys to know is the migration. Migration refers to the movement of hydrocarbon, oil and gas from the source rock to a reservoir rock where they can accumulate and be trapped. There are three types of migration. The first one is the primary, is the migration from the source rock into adjacent permanent rocks. Basically, the increasing pressure and temperature, the generation of oil within the source rock will increase the pressure inside of it. So it starts to make micro fractures that can interconnect. So they will create flow channels. So the oil can flow from the source rock to the reservoirs. I'm sorry. Hello? Hello? Hi. You hear me? Yes, I can hear you, but I closed the meeting accidentally. Can you join again? Oh, what? I'm sorry? So, should I stop? I'm in the meeting.
I don't see you. I
Uh,
don't see you. Maybe it's another meeting. Okay, give me 1 second. I will, okay, continue the meeting. So sorry.
okay, are you guys hearing me?
Hi. Yeah,
How many,
Alejandro
how
here.
many people
Yeah,
do
we
you
can
have
see you
before?
and hear you. There is
Uh,
not any problem with the presentation. I can see it well,
okay.
and I hear it well. So maybe
Sorry.
hearing it.
Carolina called me. I thought you guys were not seeing my screen.
Yeah. The situation is like the two of us have a little problem with connection, so we are going back and forward. Like, hey, check out, because well, things happens. But yeah,
Yeah,
everything
that
is
that
good.
would be fun. The recording.
Yeah, the recording is going to have like a lot of bloopers. But yeah,
Okay.
yeah, keep going. Sorry for the interruption.
No worries. So for you guys seeing the future, I'm sorry. That happens in live classes, I guess. Uh, but don't worry about it. Um, I
Yeah,
thought I was
thank you.
talking about microfractures in within the source rock,
Yeah,
and again, this generation inside the shale increase the pressure, so create microfractures. So this leads to channel flow. So, for example, the oil can go from the shale to the reservoir rock, and we call that primary migration. And the secondary migration is basically the the movement of hydrocarbons through this permeable rock until it finds a trap and it gets accumulated or it finds the surface. If somehow, in some way, this surface, this trap is perturbed or open again, this oil will flow through to a different reservoir, and we call that tertiary or remigration. But we don't discuss that much. Uh, I don't see many discussions about it. The main topics are related to primary, secondary migration. One interesting topic is the difference between long and short distance migration. The distance of how far your oil will flow, it would definitely interfere in the quality of the oil because um, if this oil is moving too far, you may lose a bit of the oil in a way. You can alter the composition, lose some of the lighter elements. That may happen some biodegradation. So when the oil flows for too long, sometimes it's more likely that you won't be able to find high quality oil, even though you generate a high quality oil. So, but that is less common to work if you have a short distance migration. So the last process that I want you guys to know is the formation of traps, and which are basically geological features where a structure of a shape of rock layers that will able to retain hydrocarbon, preventing them from migrating to the surface. So again, oils and any other fluid will trying to flow to reach the surface because it's a lower pressure area and is going to until it finds a barrier or a seal. And there are many traps, types of traps. These on the top we call structural traps, and they form from some structures that are formed in the basin, some related to tectonics. For example, this is an anticline, and the top of anticline is a lower pressure area. You can deform by faults, and these faults may also act as a conduit for oil migration. And the organization of the layers may form also lower pressure areas. There are some traps related to allokinesis. So salts deform the 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 strata, and you can create um, lower pressure areas in the flanks or even here. And we also have stratigraphic traps. Basically, the organization of the layers will and the deep of them will create lower pressure areas where the oil and gas may flow. There are also mixed traps, and basically it's the combination and of these different structures. Basically, you may have a fault and also an erosion occurring on. We call that mixed traps. So this is an example of a petroleum system. You're seeing here in gray and white source rock, and basically this depth right here is where we call this the start of oil window. Basically, what might be happening here is where you have the temperature that starts oil generation. Above that, the temperature and pressure are not high enough so you can generate oil. So that's why you only find oil source rock here in this gray area. And with increasing pressure and temperature and time, you will be able to generate oil in the source rock. That will lead to the creation of microfractures, and that will expel the oil from the source rock from this carrier bed or the reservoir. We'll call that primary migration, and the secondary migration will happen here in this permoporous rock or through the faults, and it will flow until it finds a seal or a stratigraphic a trap where the oil will accumulate. And finally, you will be able to create this events chart, and this is for this fictitious petroleum system. And basically, it is a way to organize and visualize the process and the elements that are necessary. So you can have a petroleum system. Here you are seeing their formation along the geological time. This is a way so you can better visualize when the formation of these elements happen in a basin, and that will help you to better find, to have more success in your art exploration. You can also classify petroleum system in different ways. It can be speculative if you don't have much data. You have some initial thoughts about it, and we call that petroleum system speculative. It can be hypothetical if you start to have some data and you are able to find some key elements, but not all of them in your study area. But when you get proven that every element and process have happened, we call that known petroleum system. It is already proved. So let's move on from. So that's let me see, from how we go from a sedimentary basin to a prospect. Basically, we start. This is the Campos Basin. Is an example that I wanted to guys brought for you guys. And then we start with regional studies. Again, indirect methods, mostly seismic interpretation, until we find some interesting structures that you believe that will be able to accumulate petroleum. And then when you will increase the resolution of your studies, you are going to have a petroleum system, which is basically this set of elements that I've told you. The source rock, the reservoir, where was the migration, when was the generation. And there are many classifications from, as I said, from hypothetical to known, depending of how your studies are going on, or how is the exploration in the basin. For example, in the Campos Basin, I'm talking about the post-salt petroleum system. So basically, the oil was generated here, and by migration, it flowed to it find reservoirs, turbidites in the post-salt. If you find a promising area and you start to do economic evaluation, that will lead you to define a play. So it's a promising area when is well configured, so you can have oil and gas accumulations, and it will be a good region for exploration. If you increase the resolution and minimize the uncertainty of your studies, you have a prospect. So you came from a sedimentary basin, petroleum system,
Excuse
play.
me, Andre. Sorry
Okay,
for sorry for interrupt, but it seems like the screen sharing was cut and we are seeing the migration chart.
okay.
Could you share the screen another time so we could fix it?
Is it okay right now?
Yes.
Okay. So it might actually have, I don't know if you guys saw this event chart. Did you?
And I think not, at least I didn't see it.
No,
Okay.
presentation it stops when it was about migration and it was I
Here.
don't yes there right there.
Okay. Sorry, you guys from the future again. So thank you for letting me know, guys. So this is the formation of traps. Is those are the examples that I've mentioned to you. I'm just going just very quickly. So this is an example of structural trap here with the anticline and the fault as well. So this is like a tectonic deformation that will create lower pressure areas that may happen also by the deformation of salt that in the flanks create low pressure areas. They're also here on the top. So it depends of the migration within your basin. We also, if the strata, the organization in the tip of the strata can create these lower pressure areas where oil may migrate. And you may also have these mixed traps, as I mentioned, when some of these process or work together to create these low pressure areas. So this is the petroleum system that I was mentioning. So this here is the difference between immature and mature source rock. This, what you see here in gray, may be happening by the difference of temperature or pressure. Here is when it's getting the oil window. So temperature is high enough so you can transform organic matter in kerogen and later into oil and gas, and which is not high enough here. So that's why we consider immature source rock. With the generation, it creates micro fractures and the oil is expelled from this carrier bed source rock. It can be to a reservoir fault, reservoir rock right here, or a fault. And in green, you're seeing the paths of secondary migration, and it will flow until it finds a trap, a source rock, a barrier that won't let this fluid to flow through the surface. So this is the event chart that I was mentioning. This is a nice way to organize the events, the elements of your study area. So here you see the different elements that are necessary so you can have a known petroleum system. And this is a way so you can better organize how they happen through geological time. So this is what I was mentioning from a sedimentary basin to a prospect. So this is the campus basin. So we start with regional studies, mostly seismic interpretation. And then when you go to higher resolution studies, and you find these elements and processes that I'm mentioning to you, you have a petroleum system. In this case, I'm bringing the example of a post-salt petroleum system where you had the source rock below the salt, but it was able to migrate to define reservoir rocks in the post-salt turbidite. So this is an example of a post-salt petroleum system. You know all the elements that are necessary so you can have that oil and gas accumulation. And if we again go to even higher resolution and reduce the sanctity of your studies, you'll be able to have a play, which is a promising area within the petroleum system. In this case, is a post-salt turbidite play, and you start to know if this exploration is economic valuable. If you even increase the resolution of your studies, you can get something like that, which is the prospect that you are going to drill and you plan to produce. So you are going from very low resolution studies to things that have around 20, 30 meters of width. So it also starts from, you reduce the uncertainty of your studies when you do a process like this. So what I want to talk now is how we go from these regional studies to high resolution facies rock studies. Basically, we have a couple of indirect methods, some direct methods, and it's again a combination of disciplines that I mentioned, of chemistry and geology, maybe geology and physics. They're all linked, so we can get the best results, so we can bring those results to our previous model, and again reduce the uncertainty, the errors of our studies. We're going to start with indirect methods, basically seismic first. Seismic uses seismic waves to image the subsurface structure by examining reflections from underground layers. Basically, we have a source, and this source creates a seismic wave. It gets reflected from a surface below the ground, and we have a detector that will see what was the intensity, how long it took for the wave to return. Everything is well documented and analyzed, so we can create an image of the subsurface. So there are two ways so we can acquire seismic data. We have marine and onshore. This is a short example of marine acquisition. We have boats that travel at a very low speed, and they have these hydrophones and streams that are basically microphones that are record, and these the ships will have an air gun that will create with compressed air, creates the seismic wave, and it gets reflected by the subsurface layers. And again, the time it took to get the reflection, the intensity of that reflection is all recorded, so they create image from the subsurface. In this case, to have accurate data, there are some conditions that may interfere. For example, storms, water currents, everything have to be planned and have to be adjusted so you can have a quality data. And also we have a very precise GPS, so the ship may follow through the right direction. We also have onshore seismic acquisition. Basically, the process is the same, but in this case, we have a vibrator truck or explosives. They are detonated, or this vibrator truck produces by vibration a seismic wave, and we have microphones that are fixed on the surface. This will be the source that will create the seismic wave. Then again, will be reflected by below the surface, but the subsurface layers. And then the angle, the time, and the intensity will be recorded so it can create this image of the subsurface. We have to realize that the position of these microphones is very well planned, because differently from the marine acquisition, where the ships the ship flows to a same direction. Here we have problems of vegetation, topography, and there are a lot of things that may interfere in the quality of data. For example, cell phones, towers, or even animals that can produce, if they are walking closely, they may interfere in the seismic signal, and they may reduce the quality. So this is a very manual, because as soon as they position the microphones here, they have to remove and put on a different location, and to make the same process again, so they can create a long seismic line. And there's a lot of things that may reduce the quality of data, and there's a lot of procedures, mathematical equations that may help that. And you're gonna have a whole lesson about seismic, so don't worry about it. And the next professor will go much deeper into it. But what I want you guys know is that basically seismic investigation is based on two things. On a wave, when it's propagated below the ground, firstly there is a refraction when it gets a boundary from layers from different densities, with basically the velocity changes for the wave propagation in different layers. And also part of the wave is reflected when it reaches these different layers of different rocks with different densities. And we have this equation here. Basically, what it's trying to say is that the bigger the difference between the density, the higher would be the amplitude, the reflection of this, the intensity of the reflection of the seismic signal that is going to be recorded. So this is an example of different intensities of the signal that is recorded by the detector. And if we have different microphones aligned together, we combine all those to create images similar like this. And if we put some processing methods, velocity models, we transform that in the seismic session, when you can see the organization of the strata. We can image some structures. This will be your first study, your first object of study, so we can go to lower resolutions. That is 3D and 4D seismic data. We were only seeing 2D at the time, and for the 3D, basically we are seeing 2D seismic lines very close to each other in one direction, and also there is an acquisition in a perpendicular way or close to that, and the amount of lines in these two directions and very close to each other help us to get a volumetric data acquisition and a 3D view of structures in subsurface. That is also 4D seismic, and basically in 4D we are bringing time for the equation. So we are acquiring seismic data, 3D seismic data in the same area. So this is an example of CO2 injection in saline aquifers. So here's in the 3 years, 10 years, 2 years, 12 years, 14 years, and 16 years of injection. So let me see if I can start again the video. So basically what you guys are seeing is that the migration of CO2 on this reservoir. So they are injecting CO2 on this well, and along the time the CO2 is migrating away from the well. So this is it's the same procedure to acquire the data, but they have been doing from different times. So you can see the differences along the difference on the reservoir properties in the fluid along time. You can do it for hydrocarbons as well. There are very specific studies that you can do that are very important when you are producing in the basin. This is a very nice slide. I really like that slide. I got from my advisor for my master's. He's very careful. What I'm trying to say here is that you have to be very careful with the method that you are using. Seismic is used for lower resolution studies at first. So this is basically telling us that a seismic horizon, or just one line in a seismic, in this case, it reflects the average of 38 meters of rocks. So if you guys imagine when you guys are in the field, 30 meters is a lot. That's like a building of, I don't know, maybe this is even higher than the Christ of the Redeemer, the statue that we have here in Rio. So there's a lot of heterogeneities that you have this interval. So you have to know the limitations of your data. Seismic is a very important method. It's really helpful, but you have to know for what you are using. And for you to use it in a reservoir scale is very specific, the use of seismic in reservoir scale, but it has to be combined with some other methods. So you can reduce the risks of error and uncertainties. One way is that petrophysics. So before we had the seismic and we choose to drill a well, okay? So this is an example of a drilling well, and the drilling fluid is coming off the drill bit and going to the surface. And this is the interaction of the drilling fluid in the reservoir rocks. And basically, as soon as we finish to drill, before we cement, we put equipment on the bottom of the well and we bring it up slowly with some different equipments. And these equipments will be able to measure physical and chemical properties of the rock and their interaction with the fluids. There's a lot of equipments and a lot of properties that can be measured with this equipment. And again, you're going to have a whole class about it. This is my field of study. I'm mostly specialized in petrophysics. So that's a lot that you guys are going to talk about. I'm pretty sure of that. But I brought some examples of what we call well logs. But I'm just going to go very quickly because you're going to have time to really dive into that later. So basically, caliper measures the diameter of the well. Basically, when you have a drill bit of a certain diameter, it's expected that that well is going to have the same diameter, unless you have some caving, you have the creation of mud cake or slothing. And that's important to know for geotechnical studies, and also for the uncertainty of if your other measures are in a region of caving, that may compromise the other measurements from other well logs. There is the gamma ray. Basically, it measures the gamma radiation that comes naturally from some rocks. Basically, we know that shales they have a more amount of uranium, thorium, and potassium in their structure, so they produce naturally radioactivity. And with that log, we are able to distinguish shale formations from non-shale formations. We have resistivity logs. Basically, it measures the resistance of the rock to flowing electric currents. So that's actually helped a lot us to determine where we have oil, because oil is very resistant. It's a very intervals that are rich in oil, they present very high values of resistivity. Differently from reservoirs, we have water, because all the formations below the ground, the subsurface, they have water. Some have more oil, some mostly have water. So these intervals that we have higher resistivity will help will lead us to investigate a bit more because they may be reservoirs rich in oil. So this is we have a bit more and some of models that we have here. We also have density, basically some tools that help us to measure the bulk density of the formations. And of course, if you have two sandstones, one more porous with more empty space, we have a lower density. And we also have neutron that will help us to measure the hydrogen content and basically help us to measure the porosity of the rock if there is any fluid. They are commonly used together, these two tools. And we also have the sonic. Basically, we propagate the sound wave through these rocks, and we measure the time that it takes to travel. More cemented, more closed rocks, this wave travels faster than very porous ones. So that will help us to know a bit about the porosity. But also this well log is very used to create a connection between seismic and well log measures, because commonly seismic are acquired in time, and because the wave travels to the surface and is reflected, and we measure time, and there is some equations that can transform the velocity of these waves. We can correlate and create what we call seismic well time. So basically, we can bring this measure the depth of the well through velocity. So we can tie this thing together, and again, we will refine our seismic studies with data from the petrophysics. So here's a real example of my home state. I don't know if you guys are too embarrassed to talk, but this is an example of two sandstones that one has oil and one has not. And are you guys comfortable to share your opinions, which one of them has oil or not? So basically here we are saying the gamma ray. So lower values in gamma ray indicate that it is non-shale. In this case, I'm presenting already that is sandstones. Here we have the resistivity. So we have increasing resistivity right here until this depth. Here we have the sonic, and here we have the density in blue, in neutron in red. Any idea which one has oil or not?
Well, if anyone wants to talk, to go through the chat and I read the question. For myself, I think it's the lower one,
Okay,
but
why is that?
I'm a little bit.
No, no worries about it. We're here to learn a bit. In this basin, this is the main reservoir, but this one doesn't have oil. In this specific this well, there is a well very close to it which has oil, but not in this case. And the key thing that you should see is the resistivity, which is very low here, and that basically because the reservoir is filled with salty water, which is very conductive. So since here is the resistivity, until it gets here, and the log is reading salty water, so it's very conductible. In this case, if you imagine there are similar properties here, the resistivity is way higher, and basically because oil is a very resistant fluid. So here we have a reservoir rich in oil, here rich in water. You can imagine this interval right here. Again, if you have something that is cemented or if the pores are very filled, you can get something like this, but you cannot have, it's not usual, and you're not going to see very commonly water above the oil, because oil is less denser than water. So if you're going to have in one reservoir oil and water, oil should always be, is going to be on the top because it's less denser. Firstly, gas, if you have gas, then oil, and then water. So also a tip here is the occurrence of oil in black. And this is a common, we call composite log. So this is a very common document that each log, each well has, where they present the the measurements of the logs along the depth. So here we have a 90 meters depth. Here is way lower in the 1800s. So this is an example of a real data. We in the books, everything is much easier. So I thought it would be nicer for you to have a look at what it happens in real life. And also cool example here is a very is a reservoir from eolic and fluvial. So we have very low amounts of shale. So that's why the gamma ray is very low. And if you know how those deposits are formed, you will better understand why they have such a lower amount of shale. The idea is that if you know how this deposit were formed, you better understand their properties, and you have a much higher success. Every information that you have in your model is important to reduce the uncertainty and risks of mistakes in oil exploration. But again, we had the seismic, we drilled a well, and in this case, we got the actual rock. The drill bit is not crushing the rock, but we use a different equipment that we were able to get the rock from the subsurface. So those rocks are preserved, and we can use from different studies. So this is a conventional core. This is a side core, which is basically after the well is drilled, there is equipment that take these plugs from the side of the borehole. These are the drill cuttings that is the result of the crushing of the drill bit and the fluid bringing those to the surface. We can study those as well. And these are thin sections that are made from these kind of rocks. From direct methods, there are a lot that can be done depending on your main goals. We're going to talk about organic geochemistry and rock physics, but those others as well as important. I don't know what you guys are going to do at all in IBA from these direct methods, but each one of them will help you to provide a more sophisticated, more correct model, if I should say that. So in organic geochemistry, the idea is that to understand better the source rock, so we can understand better the generation potential of hydrocarbon, and we can evaluate the quantity, the quality, and the maturity of organic matter. There is a lot of studies again that can be done. In this case, we are talking mainly about three. This is a total organic carbon. In this case, we have a rock sample, we crush them, and we put some acid to take the inorganic carbon, and we put in this equipment, and we start a combustion. And this equipment will measure the amount of CO2 that is capable to generate in this combustion. And that will be translated to the amount of the organic carbon that the source rock has. If it is a number higher than 1%, we consider with a good potential of generate of a good source rock. And there's a lot of other things that can be measured, and it can be combined with many other results as well, but the idea is that you measure the amount of organic carbon in the rock. There is also a very important one, which is called pyrolysis, rock eval pyrolysis. Basically, you put a piece of the source rock in the oven and you start to heat things up. The idea is you're gonna accelerate the process that happened in the nature. And then you measure the amount of hydrocarbon that is generated here at 300 degrees. And this was called S1, basically is the hydrocarbon that is already generated by this source rock. Then you progressively increase the temperature until you get the peak of generation and you get that temperature. And this is like the potential of hydrocarbon that can be generated for this source rock. And this is the amount of CO2 that is later generated. There are also other aspects that you can measure, but basically you're measuring again the quality of the organic matter, if it's the originals or if it's from marine source. And you can combine these here to, again, create a more sophisticated model. And there are many other analyses. In this case is vitrinite. There's a hard word to say in English, but basically is an organic compound that you can measure in a microscope, and you put a light to pass through it and you measure the reflectance. And this again will help you to understand the maturity of the source rock, but this is mainly used for terrigenous organic matter. And then when you combine this information, you can create something like this. This is a real data again. This from Egypt. I'm not sure, but I'm pretty sure that's on the Egypt. So here in this case, this percentage of generation rate, and here is the through geological time. So where you expect you got the main generation and the amount of generation that you have in your basin. So you're gonna find you try to find these source rocks. And also, if you combine this to a temperature model, this is the story of the those. This like would be the thermal history of your basin. So if the basin got at the temperature that was high enough for generate, at which formations got into that oil, we call oil window. Again, as I'm always saying to you, these are informations that will make your model more sophisticated and reduce the risk of mistakes, because finding oil is very hard. Once you get the course of the reservoirs, there's a lot of you can do as well. There's a lot, but here I'm dividing two categories, which calls routine core analysis and special core analysis. And you can measure porosity, permeability, water saturation, capillary pressures. This is information that will help you to get the water saturation, the amount of hydrocarbon that you have, the real porosity, because before we were talking about indirect methods, now you are actually measuring the rock, and this will help you to do a very well argumented supported petrophysical evaluation. And then we can go from this sample to an upscale. You can propagate this information along your study area from the sample that you have from one specific reservoir from the well. In this case, I'm talking about helium porosimeter. Basically, we dry a core sample of 1 or 2 inches, and then we put on this equipment, and they will start to inject helium, and the amount of the helium that is injected and the pressure until we get pressure equilibrium, that those things are measured, and this is a way so we can calculate the porosity in samples like that. So I'm kind of ask you to excuse me, because this is the only slide that is in Portuguese. I got this again from my advisor. and I had the time to translate to English, but I really like this one, and I thought it would be interesting to show you to you because it's you have to be in mind that it's a matter of scale. But what I'm trying to say that every method has a limitation and has a goal. When you're talking about basing scales, really large areas, you are going to use seismic to start your study because the vertical and horizontal resolutions will make you do that. When you go into reservoir and facies studies and thin sections, you're going to have different methods and different techniques, and all of them will combine to a more sophisticated model. But you have to know the limitations of your method and the goals of what are you trying to see with this method. So uh, different goals are going to need different methods. And that's what I want you guys to take from this slide and use in your experience in the IBA. You have to pay attention what is your goal and what is your method, the limitation of the method, and how you can uh, go on with that limitation, how we can reduce the error and the mistakes that are inherent of that method. And then mostly you have to combine two different things. So we're about at the end of the presentation. This is a case study that wanted to bring it to you. This is an article that came to me, I put my eyes on a couple of days before preparing this presentation. And I want you guys to know what real data looks like and how we can combine different methods. So this is in the Egypt, Western Desert of Egypt. There is this small area right here. We have a couple wells that have been drilling, that have been producing. And the idea of this study is to propose a different prospect. So this is a stratigraphic chart. So this tells us from older to the newer ones, the formations. In green, we are seeing the occurrence of oil. In red, the occurrence of gas. In yellow, what is unproven. They maybe there might have gas, but it's not have been proven yet. And these black flags tell us about the source rock. So it's a pretty known place where they have been producing oil. So as I said before, we go from indirect methods, low resolution. This is a seismic interpretation. And then you're going to have a class of how you interpret seismic lines. And in this case, they are looking for this formation right here in dark pink, which is the main reservoir they believe that may have oil. And you can see again how these layers are organizing, creating low pressure areas where the oil may migrate. And here you see a map of this, the depth of this surface right here. So basically what in red is where the surface is shallower, and in pink where it is deeper. As I said before, oil wants to flow to the lower pressure as wants to flow to the top. So that's why all the wells are drilled here in this shallower area of the formation. So here's an example of a you may see in the software of this. This is like a similar thing, a different way to see it. You're in white, you're seeing the main faults that are structuring this area. It may act as a conduit to fluid migration or may structure the basin, creating traps. So this is like again a real life well log analysis. I'm not gonna go on too deep into it, but basically they are separated to you already in yellow, what is a sandstone, and that can be a reservoir that has porosity, and in green, the shales that can be source rocks or no, just fine-grained rocks. And here we see again the high resistivity and the all calculations that can be made with this kind of data that will lead us to predict if there is more oil or water. You again will be able to do that when you have a class of petrophysics. But the idea is that map right here was refined to something like that. You're not only seeing now how the formation is structured, but you're actually seeing what is within the formation, the heterogeneities, what is shale, what is sand, and what is silt. So basically, they are telling you where is the main reservoirs, so you can explore that are actually seen in yellow. And again, there's in these kind of models, you can put a lot of properties, a lot of things you can calculate with this kind of data. It's depend of your goals. And he refined the method again. In this case, he's talking about porosity. So in pink, you are seeing non-porous rocks, and in the other colors, you are seeing a bit of porosity, effective porosity, and in yellow, the most porous areas. So again, not only he's telling us where is this reservoirs, he's telling us where are the better properties of reservoirs. And this comes first from the seismic, then from the study of the petrophysics, and then a combination of both. You can create something like this. And finally, he's calculating the water saturation. Water saturation is something that you will learn more a bit. So basically, every rock below this in the subsurface is filled with water. So if not water, what it is inside of those rocks? That may be gas, it may be mostly gas or hydrocarbon, depending on the area. So basically, they are not again telling this. He's refining the model again. He told us where is the best porosity. Now he's telling us where he has calculated oil. In blue, you actually see where is only water. In the other regions, you see where the wells found oil and where he expect to find oil. And finally, he creates a chart based on the seismic and based in everything he had done. So this is like the different formations. This is the main source rock. So these are the faults that may act as a conducts where the hydrocarbon may flow until it gets these reservoir rocks right here. So in green, you're seeing possible oil accumulation. In gas, or in red, gas accumulations. So again, gas is less denser, so it flows first. Then we have the oil, and when you have traps like this, we find you may be able to find hydrocarbons. And finally, again, this is a very to get to a map like this, there's a lot of data that we are not able to see if you just look at this map. So to make something like this, you must have a lot of arguments, a lot of conclusions, a lot of data, so you can set the prospect a better position of your what you believe is the prospect that you should drill a next well. So again, this is the map of the top of the reservoir rocks. This is a very shallow area where he calculated that it has good porosity, good permeability, and good oil. And one last question, if you guys are not too shy, just so we can end the class, I kindly ask you, imagine that we have followed everything correctly. We got the seismic well interpreted, we calculate everything correctly from these wells right here. and we are proposing a prospect right here. So it's a very close region. There's a distance that you may count, but it's a very close. So I ask you, if success is 100% guaranteed if we drill a well in this prospect? Alejandro, any suggestion, or anyone else? So basically, there is not 100% chance of success until we drill a well. Even though we had the most refined models and the most advanced data, we're going to be able to prove if there is oil if we drill a well. Nature is a very complicated thing, and you do the best to reduce the risks, but to drill a well and it comes dry, it happens. It's uh, something of the process, and you're gonna have to use the data to work harder and refine your model to propose another prospect so you can have success. So that's what I planned to talk to you today. Thank you very much. If you have any other questions, I'll be happy to answer.
Thank you, Andre. Now we are entering the question part of the session. Please, if you have any comment, any question, leave it in the chat and we can read it about. So I read here a comment from Alejandro Gomez. Since it is your area of expertise, do you recommend any book of petrophysics?
Yes, I do recommend one. I'm not the best one with names, but there is any other question because I can find it right here quickly.
I don't. I got kicked out of the room, so maybe there is any in the chat I couldn't read. I think there is a question right now. Hello,
Okay.
and from Daniela Sanchez. Can you recommend any books on structural geology?
Yes, one really nice one is Hanko Fossen. It's called Structural Geology. The author is Hanko Fossen. If easy to find with the last name Fossen. Hanko Fossen. He's a very he has a very good way to describe the structures and the process. So I really recommend that one. He also has a website. I don't know if it's still working when he create models that what is described in the book. So it's easier to see the deformation of the rocks when with these models. So Hanko Fossen, structural geology, is a very nice one.
Okay, so you could leave the name in the chat so they could get it. And guys, when you ask a question, will be a little more fun if you say, where are you from? Maybe we've got some question, I don't know, Argentina, Peru, Bolivia, Ecuador, you could say. And at least for myself, there's always questions that we'll think about it and never ask. But
Mhm.
if I'm imagine if I'm a student in my last year and I want to work as a petrophysicist when I'm older, what advice would you give to that person?
Um, I'm sorry, can you ask the question again? It got
Okay,
a bit for me.
okay. If I want to be like you, what is the best advice that you will give me? Like courses, talks, APG, start studying, get some experience in drill first, anything like that.
Okay, so I don't know if you want to be a petrophysicist. Basically, in my experience, wasn't too easy to find good courses or good professors in the areas. I had some, I had to be honest about it. But my university was not that into that kind of data, so it was hard to find projects. So you have to be very in touch with anyone that works in the area that you want to do your final dissertation in petrophysics, that will make you to read and learn about it. And once you go know someone that works in the area, that will lead you to know other persons that work in the area, that will lead you to know chapters where other professionals chat to each other. So basically, the main advice that I should you is be close to people that work what you really like. I can mention you courses, I can mention you classes, but you only gonna be known if you work together with this kind of persons, because they can introduce you to other professors, to other universities, and that will make your way a bit easier.
Okay, that
Um,
opens a new question that many students I know. I was there at one time, like 1 year ago, is how do you see the environment? Because many students have the problem that they are first generation geoscientists and maybe they don't have the tools, the contacts, what should they do?
okay, that's a very hard topic, and um, okay, don't get my answers as truth. I will just say what had worked with me. Um, for me, I needed to find some professor that worked in the area that I wasn't very close to, but I had to make a contact. That professor led me to my first research, and I worked really hard. I publicized one article about seismic interpretation. That was a cool article in an international journal, and that let open some doors to me, so I could access other professors for other universities. So if you again try to make contact with professors that working in the area, that the best advice that I want that I could recommend. If you have nothing, that is going to be hard. Uh, there's a lot of books, there are a lot of articles about petrophysics or any other method that you want. You could email an author. You may want to say that you want to work within the masters. Sometimes there are scholarships for masters. That happens here in Brazil in the lab that I work. We have some scholarships, so it will be easier for you to study and live from what you live for in your masters. But basically, that's it. Get in touch with the professors, see if there are any scholarships, and trying to learn as best as you can from the opportunities that you have. Sometimes you're going to have to create this opportunity. Sometimes life is not going to give it to you, and very sadly. So I got the book. The name of the book is called Well Logging for Earth Scientists, and the authors are putting here in the chat.
Well, here in the chat we have a question from Mauricio Hidalgo. What did you mean when you mentioned that seismic is for low resolution when you show the slice with the seismic wave and the layer thickness of 36 and 76? Greetings from Mexico.
Okay, great question, Mauricio. It's nice to see people from around the world. I would love to visit Mexico sometime. And when I'm talking about low resolution, it's because when you put a seismic wave, um, to see very deeper areas, you have to put low frequencies. When you get a very high frequency wave, you're gonna have a good image of the shallow parts, but you're not gonna be able to see very deep areas. And sometimes your reservoirs is a very low. So that led to you resolution of the seismic. So each line that you have is going to be something related to 36 meters of rock. And by low resolution say that that's a lot going on within these 36 meters. And but in seismic you're only seeing one line. So if you want to say, for example, if you want to refine a reservoir within that 36 meters, you're gonna have to go to high resolution studies. So you're gonna start from the seismic, and then you're gonna use petrophysics or rock physics from raw core. Basically, by the way you acquire seismic data, seismic is a much lower resolution study than the actual one. They can work together, but when you're using seismic, you're mostly talking about big areas, a very uh, uh, a very large interval, you know. Um, that's it. I don't know if I'm okay. I'm
There is
putting the
a sequence question from Mauricio, and I want to ask if you could share your email in the chat. That will be great. Thank you very much.
Okay, I'll be happy to share my email, and if you guys want, you can send me a message at any time. I'll be happy to help you with anything. When I was studying, there was a lot of students, a lot of professors that helped me along the way. So I'll be very happy to retribute and help you with anything. I sent the name of the petrophysics book in the chat as well, so you can check it out. There's my email, and also for the person who talked about the structural geology book, I put the name of the author here in glass. It's called Hanko Fossen. It's a very nice book. It's a good way to start of this very complicated thing called structural geology. Yeah.
Well, I think that's it. Just for the fun, that book is written by Andre Singer.
Let me
Oh,
see. It's Julian Singer and Darwin Ellis. Those are the photos here.
no, I'm just saying because I got a professor named Andre Singer at university. He was a geomorphologist, and like
That may be a coincidence, but this is a good book. There's a lot of it describes a lot of the well logs, the principles, and the differences. Is a good way to start. If you want to be more sophisticated, then you go through scientific articles. But to start to develop a study to understand how these tools work, this book is a great way to start. And again, if you have any questions, you can send me an email. I'll be happy to answer. I don't know if it's I see a question, Danielle. I'm not the one who is recording, but I'm pretty sure they will be able to share. Please get in touch with them. I thought Alejandro had a connection problem. Uh, I'll be here if you guys did, ready for him to come back. But that's what I had to present today. Hopefully you liked. And good luck in this IBA. It's a very good opportunity. So please enjoy the most and ask as many questions you need to for the other professionals that are going to be presenting later. There is also the chapter of young professionals of AAPG. That's a good way to meet different professionals. I'm the secretary of the Brazilian chapter. Probably your country has a chapter as well. That's a good way to meet people. They share the experience, they share other opportunities in the industry. So please get to know different people. That will help you a lot.
Thank you so much, Andre. On behalf of the AAPG, we are so happy to have you as a trainer. And we are hoping everybody here in the call to register to the IBA program and to keep up with the training. We have 17 talks coming up. I just send you in the chat the link to register to all. And well, we hope to have a winner here in the region, in the Latin American and Caribbean region.
Please let me know if you
Yeah, when
if
it's
we had help you about it.
presentation. And please, if you could open the camera and let's take a picture of the session. Let's try. We are like all in our cell phones. Be a little bit hard. I see over there. Let's see. Juan, please open your camera. I'm going to read all the names that haven't opened the camera.
Who's going to take the
Yeah,
picture?
you see, and they opened the camera right away. And I think we could all try to take the picture and we send it through chat or a group because I think we have really a strange connection.
Okay, please send it to me. I'm not very good with Zoom.
Okay. Yeah, guys, if you could put the photo, smile.
Please let me know if you got it.
I got it. I got some. If if you could got it too, I'm not gonna lie. I would be happy. Okay.
Okay.
Well, I think that is enough. And thank you guys. Thank you all for coming. Remember, if you want to be eligible to have the certificate, you need to enter 75%, 75% of the training sessions. This information is gold. This information is better than courses that you need to pay out there. And we also have the plus that the people that is coming to these talks, they are genuine. They really want to teach to this. So when someone has passion in what is teaching, everything is so much better. So really, I'm really appreciate you, Andre. Thank you for giving this lesson. Sorry for all the technical issues and yeah, internet sometimes.
No worries.
It's
If I
complicated.
may give you a last comment, I was missing some advice, but the IBA is a great opportunity for you to get to know other professions and learn about softwares. These courses that people are going to offer you here, they cost more than a couple thousand uh, reais and bucks. So this is a unique opportunity for you to, when you got a resume later, you're gonna be able to say that you had a course about Petrel, about many other. These are the softwares that I use every day in my research. So you're going to be able to learn it for free at a very low cost, I guess. And this will help you also to get to know other professions that have they are already in the industry. So get in touch with them and learn the software as much harder as you can because those are key aspects that you can put in your resume and you can present for a company that is being developed the software or is offering a job. So this is a unique opportunity that university doesn't always give it to you. I didn't have, and I'm pretty 100% sure that this will open a lot of doors that a person that is not doing will not have these doors open. And good luck. Hopefully you're going to win, and let me know by email if you guys want.
Well, you hear it here, guys. There is a really good opportunity in the IBA, because even for that, if you want to work in the industry or at least have a thesis in oil and gas, you're going to need softwares, and we use those softwares for the IBA, OpenBTech, Petrol, Palioscan. There are a bunch. So take it seriously, because all this program, at least when I was in the IBA, it was an investment. It was like, yeah, these are really long talks at night, but I need to go, I need to learn. I don't know what I'm going to do when I graduate, but if it's oil and gas, I need to have the information. And yeah, take it firsthand here. You need it at least later in life. You think about it, and it was like, whoa, yeah, that was worth it. That sacrifice to have to be 2 hours late at night. But really, thank you, Andre, for this opportunity. And I'm really sorry for technical issues, but
No
we
worries.
are all learning in this process. And thank you, guys. Thank you all for coming. And I hope I see you in the next session.
Bye, guys.
A
And good
good
luck.
night. And I want to say one thing. We draw Venezuela, Brazil, 1-1.
Oh, oh my
For
God.
Venezuela, this is a win.
Thank you for the bad news.
Have a good night, guys.
Me too.
Bye bye.